In Chapter 6 for our organic chemistry class, we're going to look a little more closely at different types of chemical reactions that are involved in organic chemistry and other basic types of chemistry reactions that we think about in organic chemistry. And those include these 5 different types. So we have elimination, substitution, combustion, addition reactions, and rearrangement reactions. So I would like you for this section to understand and know what these meanings are and what's happening in these 5 different reaction types. I like to use this idea of SCAR as an acronym for remembering these different types of chemical reactions. So SCAR, stupid way to remember that. And just for combustion, sometimes we also think of that as oxidation. So you could say Escobar instead for oxidation, by the way. Get it? So that's another one, but that's also kind of part of that combustion idea. So as an overview of what we'll talk about, we'll be looking at some of these different types of chemical reactions. We'll be also looking at the difference in energetics between different types of reactions depending on how they're going to proceed, what the overall energy before and after those chemical reactions are going to be. And we'll look at some of those rate constants and how quickly those reactions are going to move. Some of the energy terms that we'll look at are the equilibrium constants and the free energy, also the enthalpy and entropy, different types of energy constants and things regarding the energy that we'll look at. Okay, so for the first step, that's the general overview. And the next step is to look at how we describe multi-step chemical reactions. So let's look at some examples. Sometimes we will use these reaction arrows to say this reactant will react to form this product. Sometimes in organic chemistry, we have multi-step reactions, and we'll list out the steps on top of or below this arrow. Rather than to use this as a reactant, we actually put these as first reaction, second reaction to get to that product, to kind of condense those things. So if you see a bracket with a 1 or a 2, for example, above or below an arrow, that just means we put one reactant in, we let it react, and then we put the second reactant in, and then we let that react. So here we have sometimes we're also going to put catalysts here, and byproducts or things that are coming off are sometimes omitted. So just be aware of those different conventions. So here are some examples of different conventions again, where, for example, we'd have molecular bromine that would be written as a reactant with a plus sign. Sometimes that is written on top of the arrow just to indicate that's part of the chemicals that are used to get your product out. Here on B, we're using that more condensed version where the compound is written above the arrow, and then HV or delta is going to refer to as light. HV is Planck's constant times the nu value, or that wavelength. So we're going to be, that's light, and then delta is a change in heat. So just know these different things represent heat or light to add essentially energy to the system. And also CCl4 is an example of a solvent. So a lot of times if you don't have those bracketed numbers like we saw on this slide here, we're going to, underneath would be solvents, heat, light, maybe a different type of catalyst might be shown below as well. So these are some different conventions, so don't get confused by those by knowing some of these conventions. So I mentioned these 5 different types of organic reactions. I'm going to start with actually this middle one, substitution reactions. So here is a substitution reaction in its simplest form, where essentially substituting these 2 different compounds. So one is attached to this carbon here. It's a Z or H, we're talking about heteroatoms, so non-hydrogen or carbon compounds, right? So that's a hetero, means something not hydrocarbon. So we're talking about oxygen, bromine, halogens, different nitrogen perhaps. So we're going to substitute that off and swap it out. And you'll notice that Y substitutes for the Z, and then we're left with the Z left alone here. So it's trading places. Here are some specific examples where we have iodine trading places with a chloride ion. And then we have a chlorine molecule that's attached, and then an iodide ion that's left behind. Here we have a hydroxide and a chlorine, and we're going to replace those out. So this is a substitution chemical reaction. Next, we'll talk about an elimination reaction. And this is when we are eliminating different atoms from a molecule. And X and Y these are two different sigma bonds. So there's single bonds between these carbons and these elements that are next to each other. And we're going to remove them, and they're going to form a new bond between themselves. And then we form a new pi bond is formed between these carbons. So now it's a sigma bond, and we're going to break these bonds to create a new pi bond between the two carbons and form that double bond. So this is an elimination reaction because we're eliminating these two components from that molecule. Here's some examples of an elimination reaction. We're going to take one of these hydrogens, and on an adjacent carbon, we're going to remove a bromine. We're going to lose or remove HBr. We're going to eliminate this HBr. So here we have over here HBr. The reagent that we're talking about is here an example is a hydroxide. So we actually will form water, and it's a little more complex than this, right? We have a swapping that's happening, but it's essentially we're still from those two carbon atoms, we're losing the H and the Br. So we might have a different type of rearrangement. Here's an example where water is just formed. We have a hydroxide, so an alcohol group, and on an adjacent carbon we have a hydrogen. So we're going to eliminate those two elements off of those, and then we're going to form a new double bond. So we are forming water. So those of you that are in the lab this semester, we've done an elimination reaction already where we've formed a double bond by eliminating water from that ring structure. Addition reaction is, as you guessed it, adding something, and it's essentially the reverse reaction of what we just looked at. So we have a double bond, and now we're going to break that double bond to form two new sigma bonds between these compounds that are shown here, so X and Y. And here are some examples looking at this. Pi bond is broken to form a bond, a new sigma bond with a hydrogen, and a new sigma bond from this carbon with a bromine. And we have also the example of that ring again where we have a double bond. We have water here. We're going to use an acid catalyst, H2SO4, to break this pi bond and make adjacent bonds for a hydroxide and hydrogen. So we'll make an alcohol functional group now. As I mentioned, these elimination and addition reactions are kind of opposite to each other, and it just depends on if you're adding stuff or removing it to form these double bonds. Typically, they're going to in some way either result in a double bond being formed or a double bond being broken. Okay, so I want you to look at these 4 different chemical reactions, and I want you to determine if what's happening in those reactions are a substitution, elimination, or an addition reaction. And what we're going to do is I'm going to go through these answers in class the next time we meet. Some terminology that I want to point out too, and we're starting to look more at chemical reactions, are this idea of concerted reactions versus stepwise reactions. So concerted reactions are basically you just have your reactant and you have your product, and you're not looking really at any of the mechanistic things that are happening in the creation of that product, or it's just it all happens at once. Sometimes there are going to be intermediates that we're going to look at, and we're going to be talking about stepwise reactions. So that's just if we're going to show more than just your starting point and your ending point. We're going to kind of give an idea of what the intermediate steps are to help us understand why and how the products are being created. There are also different types of cleavage or bond cleavage. Homolysis is, homo means the same, right? So if we're going to break a bond, for example, between A and B, we're going to give each of these elements the same number of electrons. So we're going to break that apart. So we're going to form what is called basically a free radical. This is usually less common, and this is a higher energy state. So electrons like to be paired up if possible. So this is homolysis, where we would break that and each atom gets 1 electron. There's also heterolysis, where typically the more electronegative element is going to get both of the electrons. So if we can break that apart, and we have one of those elements is going to be positively charged, because remember, normally when we do formal charge, if we have each one of these kind of gets half of this, it gets one of the electrons from this bond. If it lost both of them, if both of them leave and go to the B element, then we're going to have a positive charge here on the A, and B is going to be negatively charged. So this helps us also balance our reaction, where we have an overall +1, -1 equals 0, and then this we start without a charge. Or the opposite could happen, where both electrons go to A and B does not get it. So it's essentially the same thing. And again, typically these electrons are going to move towards the more electronegative element. And just to show you the arrow formalism, we've talked about this before, but if we break this into two, this 1/2 or single-sided arrow represents just the movement of 1 electron. So you can see that with a homolysis versus heterolysis, where we have both a double-headed arrow, both of these electrons are moving to B. Here are some examples of this reaction happening. So homolysis, where we have a chemical compound here, and this bond between the carbon and this Z atom are going to break evenly as a homolysis product. We're going to form a free radical on this carbon and a free radical on our Z atom. We have heterolysis is another possibility, where this bond breaks and the Z element takes both of the electrons, and we get a carbocation, versus a heterolysis where the carbon here will take both of the electrons, where we have a carbanion, and then we have a Z plus ion. So these are different intermediates that you might get, and this is again the difference if we're talking about stepwise reactions, where we're looking at reaction intermediates. Those are going to be very short-lived elements. So carbocations, free radicals, carbanions, these aren't going to last very long in solution, so they'll react with something else pretty quickly. So that's where we are talking about those stepwise chemical reactions. And you can feel free to kind of do the math here for formal charge, but the free radical, even though it's a really high energy, high potential energy state, it is neutral. And this carbon, when both of these electrons leave, is going to be positively charged. And if both electrons are just carbons, then we'll have a negative charge. These reactions are intermediates, because typically we're going to have something then react. So this is going to react as an electrophile, because it is going to want to pair this electron up with something else. We'll also have an electrophile in a positively charged element, because we want this is going to be very attractive to other electrons. Here, a carbanion is going to act as a nucleophile. So it's going to want to look for a nucleus, or look for positive charge to address this negative charge on here. So these are going to be really short-lived, and they're going to be reactive intermediate species. So here's an example of resolving these free radicals or lone pairs of electrons. Typically, if you have multiple free radicals in a compound, or if you make two intermediates, these free radicals are going to resolve each other by forming a new bond. So you'll notice this single-sided arrow. We're going to point these in the middle of the two, and then we're going to form a new bond. So 1 electron comes from each to form a new bond. This will happen really quickly in solution. We also have, if we have a negative ion and a positive ion, and then one of them has a lone pair of electrons, those will donate those electrons to form a new bond to resolve that negative and positive element. So this lone pair, it's also sometimes referred to as a coordinate covalent bond. So when we have a lone pair of electron forming a bond with something that's positively charged. And just as a review for some of the arrows that we have been discussing in this class, and again, just to know the difference, reaction arrows are drawn between starting materials and the products. Double reaction arrows, we're looking at equilibrium. Remember, we looked at those when we were looking at the pKa's and deciding if something was going to go to the products or back to the reactants based off pKa values of our acids. Double-headed arrows, we're talking about resonance structures. So if things have multiple different structures, we're not moving the protons, we're just looking at where electrons are moving with the double-headed arrow. Full-headed curved arrows, looking at both electrons moving, versus half-headed arrows, we're just looking at single electrons moving. So 2 more things I'd like you to do for this video, and we'll cover these answers in class, but maybe pause this, read this question. You're going to use arrow formalism to draw the mechanisms for the products formed by heterolysis of the carbon heteroatom, so the carbon and the different atoms that are not carbon or hydrogen. And then you'll classify the intermediate. Make sure that you're giving the more electronegative element both of the electrons in the bond in this heteroatom. And so pause and then do that. And then there's one more. I'd like you to also look at curved arrows showing the movement of electrons. So where are the electrons going to move? Remember, electrons are coming from negative elements typically. So how are we going from these reactants to these products, for example? And so do your best to answer that, and we'll cover the answer in class when we next meet for these 2 learning, or these actually 3 learning checks from this video lecture.